here and to present our recent experimental work done in the group of Bloch in the Munich lab. And I also want to thank our theory collaborators here in Harvard, not in Harvard anymore, but still in Harvard at that time. So I will present our latest experimental results in the measurement of SAC phases in one-dimensional optical lattices. So I'm going to start with a short introduction. So the SAC phase is closely related to the Berry phase, which is well known to probably all of us. Just very quick. So if the system is in an eigenstate n, which depends on some parameter r, and is then it evolves adiabatically through the parameter space along a closed loop. By changing this parameter r, it will pick up a Berry phase, which I want to refer to the most prominent example, probably to all of us, the spin 1/2 particle in a magnetic field, where the spin then processes on the Bloch sphere, and the Berry phase is related to the opening angle of this evolution on the Bloch sphere. So now in periodic potentials, we know that the eigenstates are given by the Bloch waves, which depend on the quasi-momentum in the lattice. And when a particle moves adiabatically in momentum space around a closed loop, it will also pick up a Berry phase. And in particular, if particle moves around a loop in momentum space which encloses the boson, we know that in 2D this is closely related to important invariants like the Chern number that then gives rise to phenomena such as the quantized Hall conductance. Now the question is, what is the relevant property in one-dimensional periodic potentials to characterize the topological properties of one-dimensional systems? Now, this question is very easy to answer if we remind ourselves that the two-dimensional boson is the topology of the two-dimensional boson is actually nothing else than a torus, which means that 2 points in momentum space that are connected by the reciprocal lattice vector are equivalent, and if a particle moves along a straight line, it actually performs a closed loop on this torus. So we can define a quantity similar to the Berry phase in 2D, which in 1D is just the integral along a straight line between two momentum states that are connected by the reciprocal lattice vector. This is the so-called SAC phase, or the Berry phase in 1D, which gives then rise to very interesting effects like edge states if it has a non-trivial quantity and so on, which is not the main topic of this talk, but we are interested in measuring this SAC phase in one-dimensional periodic potentials. So one very prominent example of such a one-dimensional periodic system is polyacetylene, which is described by the famous Su-Schrieffer-Heeger model, which is actually very simple. It's a chain of bonds which alternate in coupling strength. We have two different coupling strengths, J and J prime, and they alternate in strength. Now it turns out that in this very simple system, we actually have two distinct topological phases, depending on if the chain starts with a bond of strong coupling or weak coupling. And the SAC phase difference between these two systems is given by pi. I have to mention here that the gauge invariant quantity is really the SAC phase difference between these two topological phases, while if you look at the SAC phase of an individual realization, it depends on the choice of the unit cell, so it's not a gauge invariant quantity. And what we want to measure is really the SAC phase difference between these two topological phases that are separated by a phase transition point at J prime equal to J. So here I show you the dimerized lattice potential used in our experiment. I will explain later in a bit more detail how we actually realize such a potential. But you can already see that atoms sitting on minima in this potential are coupled to neighboring sites by coupling strength that also alternates in strength, similar to polyacetylene. And in the tight binding limit, it's exactly described by the same Suschrift-Verheger model in polyacetylene. And so we have these two non-equivalent sites in a unit cell. We have a sublattice structure, sublattice A and B, and we can write down an ansatz for the wave function in this form, where alpha k and beta k gives the amplitude on the different sublattices. So these are internal complex numbers, and if we plug in this ansatz for the wave function in the Hamiltonian, it reduces to a very simple two-dimensional problem. And so you can see here on the diagonal terms, there's no energy difference between sublattice A and B. And the only interesting quantity here is the off-diagonal coupling, which depends on these two different strengths, J and J prime. So we can write this as a complex number, and we all know the solution of this problem. The eigenstates are simply symmetric and antisymmetric superpositions of the amplitudes alpha and beta k. And the most important property here is that the amplitude on sublattice B is complex. And I plotted here the argument of the complex number as a function of the quasi-momentum. Since we have two non-equivalent sides, the band splits up into two subbands and is symmetric around q equals 0. So now if we come back to the Sachs phase and we think about a particle that starts moving at the band edge and moves across the polar zone, we'll pick up this geometric phase given by this expression, where this amplitudes are nothing else than the cell periodic Bloch function uk, which was in the formula in the previous slide. So it reduces to a very simple form, and we see that there's no contribution from amplitudes alpha k because it doesn't depend on the quasi-momentum, but only on the complex value of the amplitude beta k. And this is given by the derivative of the argument of this complex number. And we can simply read off the value of the Sachs phase from the diagram here. We see that it's pi over 2. And as I told you, we have two distinct topological classes. So now what happens if we change this coupling strings J and J prime, if we turn them around, then it turns out that what changes is the sign of the argument of the complex value here. So the sign of the Sachs phase flips, and we end up with minus pi over 2. So that the difference is given by pi in the end. Okay, so we can also picture these cell periodic Bloch functions here as a two-component spinor on a Bloch sphere. And this is what I plotted here. So we have u minus k, the cell periodic Bloch vector of the lowest band, and u plus k of the upper band. They point in opposite directions because they have to be orthogonal. And when we change when we vary the momentum, what happens is that the Bloch vector rotates in the equatorial plane. It stays in the equatorial plane because there's no energy difference between the two sublattices. There's no reason why the vector should flip out of the equatorial plane. And the Sachs phase is pi over 2 for both the lower and the upper band, because what actually matters is the winding on this Bloch sphere. And then if we do the same for the second topological phase, which we call D2, the only thing that changes is actually the sense of rotation. So the vector rotates in the opposite direction, and we get a value of the Sachs phase of minus pi over 2. Okay, so then how can we realize such a potential with ultra-cold atoms? So we use two standing waves, where one has twice the wavelength of the other, and we have full control over the relative phase between the two standing waves. So we can adjust the relative phase such that we end up with this potential where there's no energy difference between sublattice A and B, and we have alternating coupling strengths between neighboring sites. We can also realize the second class by simply shifting the relative phase between the two standing waves and realize exactly the opposite potential, where the chain starts with a weak bond. And we expect to have a Sachs phase difference between these two realizations of pi, as I mentioned before. Okay, so now let me explain the experimental protocol we use to measure the subphase difference. So we start preparing BEC of rubidium atoms in the Q equals 0 momentum state. Then we apply a microwave pulse to create a coherent superposition of quasi-spin states. In our case, it's two different Siemens states with opposite magnetic moment. We use 1 minus 1 and 2 minus 1. And then when we apply a magnetic field gradient, what happens is that we have opposite forces in the two spin components, and they travel in opposite directions once we apply the force. And once they reach the edge of the band, they have already performed a closed loop in momentum space. So, and the relative phase between the two particles that they pick up after they did this half of a Bloch cycle has three different contributions. The first one is the geometrical phase, which I have explained you before, due to this evolution here. And the second one is the dynamical phase, which is only due to the energy landscape in the band. So it's related to the energy. And since it's symmetric around Q equals 0, these two contributions cancel. So in the relative phase between the two spin components, it drops out. And then we have a third contribution, which is just related to the Siemens energy of the atom in the external magnetic field. So what we do then is we apply a spin echo pulse to make it more robust against magnetic field fluctuations, and we change the dimerization. So we switch between one configuration of the superlattice potential to the other configuration, as I explained you before, by changing the relative phase between the two standing waves. And this has two effects. So first of all, of course, the spin flips. So we apply this pulse, and the atoms get transferred to the upper band because we do this change of the relative phase between the two standing waves non-adiabatically. So the atoms get transferred to the upper band, but since I told you before, the Sachs phase is the same in the lower and the upper band. It actually doesn't really matter if we perform Bloch oscillations in the lower or in the upper band. So then we let the atoms evolve back in the magnetic field gradient to Q equals 0 and look at the relative phase at that point. So what we get is then the Sachs phase difference between one topological class and the other, plus some potential Siemens phase, which should ideally be cancelled by the spin echo pulse we applied in the middle. And this relative phase we can then read out using Ramsey interferometry. So we apply another pi/2 microwave pulse, change the phase of the last pulse, and measure the fraction in one of the two spin components versus the microwave phase. So then let me show you first one of the experimental results. So here you see Bloch oscillations in the lower band. These are time of flight images of the momentum distribution, putting next to each other, stripes putting next to each other versus the time we apply the magnetic field gradient, the force that acts on the atoms. You see that they start at Q equals 0, the momentum evolves linear in time, and here they reach the edge of the band and reappear on the other side, and you see the typical evolution in the Bloch oscillations. And for the second spin component, second Siemens state, you see that it evolves in the opposite direction. Now, if we apply this dimerization swap, if we change the optical potential, we do this at the band edge, so at this point, and then they get transferred to the upper band, so they appear in the first Brillouin zone, and you see the same evolution, linear evolution, but in the first Brillouin zone now, because we have transferred the atom to the second band. Okay, so then we have to do some reference experiment to be sure that all our spin echo pulses and all our cancelling in phases we don't want to measure works in the end. So it's the same protocol in principle. We again start with the coherent superposition of spin up, spin down particles. We let them evolve in the Brillouin zone, but now we apply the spin echo pulse, but we don't change the dimerization. So So they are at the band edge. They have the geometric contribution, the dynamical phase cancel, as I told you before. They have some Zeeman phase acquired. We apply this spin echo pulse to get rid of this Zeeman phase, but we don't change the dimerization. So we stay within this D1 topological class. We don't change it to D2. And what happens is that the atoms simply go back, unwrap the geometrical phase again, and what we would expect in the end is to measure just zero phase difference between the two spin components, because they simply unwrap the geometrical phase again. And then we read out this phase difference by Ramsey interferometry again. And this is the result we get. So if the phase difference would be zero, what we would expect is that the Ramsey fringe starts here at zero, because we simply apply a pi over 2 pulse, a pi pulse, and another pi over 2 pulse, so we should end up in the spin down component again. And what we see is that it's not zero, it differs. And we can also explain this difference because when we measure the resonance to transfer the atoms between the two Zeeman states versus time, we see that there's some drift. So we have magnetic field drifts over this one Bloch oscillation cycle, which can then explain this finite phase difference. So this serves now as our reference fringe. And if we do now the actual measurement where we apply the dimerization swap together with the spin echo pulse, and then perform another Ramsey interferometry experiment, we see the blue curve, which is nicely out of phase compared to the reference fringe we measured before. And we also did a small statistical analysis on that, but just 14 measurements, very statistical. And what we get is like 0.97 pi, which is very close to the expected value we have. Okay, then we can do another experiment or another series of experiments by introducing an energy offset between the sublattices A and B. So this is given by this data here, transmediate Hamiltonian. And what happens is that the weight on different sublattices changes. So once we introduce the energy offset data, the vector on the Bloch sphere flips up from the equatorial plane or down, depending on the value of the tilt. And similar to the spin 1/2 particle in the magnetic field, we expect the Sag phase, the geometric phase, to go down if we increase delta, because it's somehow related to the opening angle on this Bloch sphere, similar to a spin 1/2 particle. And so now we slightly modify the protocol I told you before. We again start at Q equals 0, apply the pi over 2 pulse, create the coherent superposition, let them evolve to the band edge, so that the geometric phase they pick up is the same than before, now without the tilt still. So the first half of the protocol is the same than we had before. But once they reach the band edge, we apply again a spin echo pulse, but instead of changing the dimerization, now we simply introduce a small tilt. Then we let the atoms evolve back, and what we measure in the end is Sag phase difference within the same topological class, but having no tilt minus having a small tilt in the optical potential. And then we again read out the phase with Ramsey interferometry. So this is the result we get. So here you see two examples of Ramsey fringes. So in black, again, it's the reference fringe. In blue, you see the fringe after the protocol. Here for delta over J around 1.2. In one case, it's shifted to the left. In the other one, it's shifted to the right. So in one case, we have minus the delta phi. In the other one, we have plus delta phi. This region you can understand very easily. So at no tilt, we would expect to measure actually no Sag phase difference, because this is our reference fringe. So it's the same measurement. We have no tilt in the system. We don't swap the dimerization. We simply go back, unwrap the phase. So what we want to measure is a phase of 0. And then once we go along this line, what happens is that during the second half of the Bloch oscillation, we pick up a geometric phase that gets smaller than pi over 2. So during the first half of the Bloch oscillation, you pick up a phase pi over 2. Then if you don't swap the randomization, you unwrap it again, so pi over 2 minus pi over 2. But then when you introduce a tilt, you get pi over 2 minus something that is smaller than pi over 2. So in the limit of increasing delta, you will measure a subphase of pi over 2. And okay, the shaded area you see here is the uncertainty in the calibration of this energy offset between sublattices we have. Okay, with this I already would like to conclude. So I've shown you the measurement of the subphase. So I think it's a very beautiful result, even though it's very simple to calculate. And you also have thought about how to extend this to higher dimensions. So I would like to direct your attention to this paper by Dina Bani on the archive, and to give you a short idea of how this can work in 2D. For example, to measure the pi flux around the Dirac cone is the following. So you have a Dirac cone in the dispersion relation, let's say. So this is a dispersion relation for our staggered flux lattice we have created in an experiment. So you can imagine that for measuring this pi flux, principally you would want to do a closed loop around the Dirac cones. This Dirac cone is here. But now, similar to what I told you before, that the Brass one has a torus topology, this path is equivalent to this path. So if you don't do a closed loop, these two phases actually cancel and are not important. You don't need to measure it. The only thing that's necessary is to measure, to do the subphase experiment once above and once below the Dirac cone. And what you see, or what you would want to see, is a jump in pi in the subphase you measure above and below the Dirac cone. It can be also used to measure Chern numbers in the system, and if one has single-site control, one can create domain walls, sublattice defects in the sublattice structure, something like AB, AB, and then study BA, BA again, and study domain walls in the system and see what happens there. And in the end, I would like to thank the